This photo shows branch lightning coming from a dark cloud and hitting the ground. Figure 4 when you can use probability and discrete random variables to calculate the likelihood of lightning striking the ground 5 times during a half-hour thunderstorm. Credit modification of work CG Lightning Strike by Axel Reuven/Flickr, CC by 20. A student takes a 10-question true-false quiz. Because the student had such a busy schedule, they could not study and guesses randomly at each answer. What is the probability of the student passing the test with at least a 70%? The manager of an auto dealership might be interested in the color preferences for new car buyers. Suppose on average the dealership sells 20 cars per month. What is the probability that a customer prefers red cars? These two examples illustrate two different types of probability problems involving discrete random variables. Recall that discrete data are data that you can count. That is, the random variable can only take on whole number values. A random variable describes the outcomes of a statistical experiment in words. The values of a random variable can vary with each repetition of an experiment, often called a trial. Random variable notation: the uppercase letter X denotes a random variable. Lowercase letters like X or Y denote the value of a random variable. If X is a random variable, then X is written in words, and X is given as a number. For example, let X equals the number of heads you get when you toss 3 fair coins. The sample space for the toss of 3 fair coins is TTT, THH, HTH, HHT, HTT, THT, TTH. HHH, then X equals 0, 1, 2, 3. X is in words and X is a number. Notice that for this example, the X values are countable outcomes. Because you can count the possible values as whole numbers that X can take on and the outcomes are random, the X values 0, 1, 2, 3. X is a discrete random variable. Probability density functions PDF. For a random variable, a probability density function or probability distribution function has two characteristics. Each probability is between 0 and 1 inclusive. The sum of the probabilities is 1. A probability density function is a mathematical formula that calculates probabilities for specific types of events, what we have been calling experiments. There is a sort of magic to a probability density function PDF, partially because the same formula often describes very different types of events. For example, the binomial PDF will calculate probabilities for flipping coins, yes/no questions on an exam, opinions of voters in an up or down opinion poll, indeed any binary event. Other probability density functions will provide probabilities for the time until a part will fail, when a customer will arrive at the turnpike booth, the number of telephone calls arriving at a central switchboard, the growth rate of a bacterium, and on and on. There are whole families of probability density functions that are used in a wide variety of applications, including medicine, business and finance, physics and engineering, among others. For our needs here, we will concentrate on only a few probability density functions as we develop the tools of inferential statistics. Counting formulas and the combinational formula to repeat, the probability of event A, PA, is simply the number of ways the experiment will result in A, relative to the total number of possible outcomes of the experiment. As an equation, this is letter 1d443, letter 1d434, equals number of ways to get a total number of possible outcomes. When we looked at the sample space for flipping 3 coins, we could easily write the full sample space and thus could easily count the number of events that met our desired result. Gx equals 1, where x is the random variable defined as the number of heads. As we have larger numbers of items in the sample space, such as a full deck of 52 cards, the ability to write out the sample space becomes impossible. We see that probabilities are nothing more than counting the events in each group we are interested in and dividing by the number of elements in the universe, or sample space. This is easy enough if we are counting sophomores in a stat class, but in more complicated cases, listing all the possible outcomes may take a lifetime. There are, for example, 36 possible outcomes from throwing just 2 six-sided dice, where the random variable is the sum of the number of spots on the up-facing sides. If there were 4 dice, then the total number of possible outcomes would become 1,296. There are more than 25 million possible 5-card poker hands in a standard deck of 52 cards. Obviously, keeping track of all these possibilities and counting them to get at a single probability would be tedious at best. An alternative to listing the complete sample space and counting the number of elements we are interested in is to skip the step of listing the sample space and simply figuring out the number of elements in it and doing the appropriate division. If we are after a probability, we really do not need to see each and every element in the sample space, we only need to know how many elements are there. Counting formulas were invented to do just this. They tell us the number of unordered subsets of a certain size that can be created from a set of unique elements. By unordered, it is meant that, for example, when dealing cards, it does not matter if you got ace, 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 king, or king, ace, 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 or ace, king, ace, 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 and so on. Each of these subsets are the same because they each have 4 aces and 1 king. Combinational formula, nx equals letter 1 d4 5b letter 1 d4 3 6 letter 1 d4 6 5 equals n. X letter 1 d4 5b minus letter 1 d4 6 5. This is the formula that tells the number of unique unordered subsets of size x that can be created from n unique elements. The formula is read n combinatorial x. Sometimes it is read as n choose x. The exclamation point is called a factorial and tells us to take all the numbers from 1 through the number before the and multiply them together. Thus 4 is 1 2 3 4 equals 24. By definition 0 equals 1. The formula is called the combinatorial formula. It is also called the binomial coefficient, for reasons that will be clear shortly. While this mathematical concept was understood long before 1653, Blaise Pascal is given major credit for his proof that he published in that year. Further, he developed a generalized method of calculating the values for combinatorials known to us as the Pascal triangle. Pascal was one of the geniuses of an era of extraordinary intellectual advancement, which included the work of Galileo, René Descartes, Isaac Newton, William Shakespeare, and the refinement of the scientific method, the very rationale for the topic of this text. Let's find the hard way: the total number of combinations of the 4 aces in a deck of cards if we were going to take them 2 at a time. The sample space would be S equals spade heart diamond heart diamond heart club. There are 6 combinations, formally 6 unique unordered subsets of size 2 that can be created from 4 unique elements. To use the combinatorial formula, we would solve the formula as follows. 4 2 equals 4, 4 minus 2, 2, equals 4 3 2 1 2 1 2 1 equals 6. If we wanted to know the number of unique 5-card poker hands that could be created from a 52-card deck, we simply compute 52 5, where 52 is the total number of unique elements from which we are drawing and 5 is the size group we are putting them into. With the combinatorial formula, we can count the number of elements in a sample space without having to write each one of them down. Truly a lifetime's work for just the number of 5-card hands from a deck of 52 cards. We can now apply this tool to a very important probability density function, the hypergeometric distribution. Remember, a probability density function computes probabilities for us. We simply put the appropriate numbers in the formula and we get the probability of specific events. However, for these formulas to work, they must be applied only to cases for which they were designed. The simplest probability density function is the hypergeometric. This is the most basic one because it is created by combining our knowledge of probabilities from Venn diagrams, the addition and multiplication rules, and the combinatorial counting formula. To find the number of ways to get 2 aces from the 4 in the deck we computed, 4 2 equals 4, 2, 4 minus 2 equals 6, and if we did not care what else we had in our hand for the other 3 cards, we would compute 48 3 equals 48, 3 45 equals 17 296. Putting this together, we can compute the probability of getting exactly 2 aces in a 5-card poker hand as 4 2 48 3 52 5 equals 399. This solution is really just the probability distribution known as the hypergeometric. The generalized formula is EAX letter 1 d4 4 1 minus letter 1 d4 3 4 letter 1 d4 5b minus letter 1 d4 6 5 in n, where x equals the number we are interested in coming from the group with the objects. Hx is the probability of x successes in n attempts when a success's aces in this case are in a population that contains n elements. The hypergeometric distribution is an example of a discrete probability distribution because there is no possibility of partial success. That is, there can be no poker hands with 2 1 2 aces. Said another way, a discrete random variable has to be a whole, or counting, number only. This probability distribution works in cases where the probability of a success changes with each draw. Another way of saying this is that the events are not independent. In using a deck of cards, we are sampling without replacement. If we put each card back after it was drawn, then the hypergeometric distribution be an inappropriate PDF. For the hypergeometric to work, the population must be divisible into 2 and only 2 independent subsets, aces and non-aces in our example. The random variable x equals the number of items from the group of interest. The experiment must have changing probabilities of success with each experiment. The fact that cards are not replaced after the draw in our example makes this true in this case. Another way to say this is that you sample without replacement and therefore each pick is not independent. The random variable must be discrete rather than continuous. Example 4. One problem: a candy dish contains 30 jelly beans and 20 gumdrops. 10 candies are picked at random. What is the probability that 5 of the 10 are gumdrops? The 2 groups are jelly beans and gumdrops. Since the probability question asks for the probability of picking gumdrops, the group of interest first group A in the formula is gumdrops. The size of the group of interest first group is 30. The size of the second group is 20. The size of the sample is 10 jelly beans or gumdrops. Let x equals the number of gumdrops in the sample of 10. X takes on the values x equals 0, 1, 2, 10. What is the probability statement written mathematically? B. What is the hypergeometric probability density function written out to solve this problem? C. What is the answer to the question, what is the probability of drawing 5 gumdrops in 10 picks from the dish? Solution A. Letter 1 D443. Letter 1 D465 equals 5. B. Letter 1 D443. Letter 1 D465 equals 5 equals 35, 25, 50, 10. C. Letter 1 D443. Letter 1 D465 equals 5 equals 0. 215. Try it. 4. 1. A bag contains letter tiles. 44 of the tiles are vowels and 56 are consonants. 7 tiles are picked at random. You want to know the probability that 4 of the 7 tiles are vowels. What is the group of interest, the size of the group of interest, and the size of the sample? Example 4. 2 problem TSA officers claim that they randomly select boarding passengers for additional search of carry-on luggage. During the past hour of the 100 passengers passing through the security point, 5 were silver-haired grandmothers, of which 3 were chosen for additional screening among the 20 total chosen for enhanced vetting. Calculate the relevant probability and comment. Solution Step 1. Determine what the random variable is, or asked another way, what are we interested in? In this case, it is the number of silver-haired grandmothers who were stopped for additional search of carry-on luggage. We also determine that this is a discrete random variable because it is a counting number. Further, we determine that x can take on only the values x equals 0, 1, 2, 3, 4, 5. Step 2. What is the experiment? Here passengers are selected, we are told, randomly for additional baggage search. This would be selection without replacement. Step 3. Can the objects the passengers here be divided into at most 2 categories? Yes, here because we are interested in only the category silver-haired grandmothers and everyone else. These data can be analyzed with the hypergeometric probability density function because it meets all the requirements of that distribution. Step 4. What is the question asked? Unlike example 4.1 about drawing candies from a bowl, there is no obvious question being asked. The candy bowl problem is mechanical with an obvious question directly stated concerning the probability of drawing 5 gumdrops. In short, an obvious question with no implications. Do we really care about the probability of drawing 5 gumdrops? Here there is an interesting question because the security office made a claim that we may indirectly test using simple probability. The security office claims they randomly select passengers for enhanced vetting. From the data we see immediately that of the 5 silver-haired grandmother passengers, 3 were selected for additional search. This is 60% of all silver-haired grandmothers. We can form our own question to determine the probability of selecting 3 of 5 in this category of passengers if we are selecting randomly. Remember that random selection means that each object has an equal probability of being selecting. Our probability question in words is thus, what is the probability of selecting 3 silver-haired grandmothers from a group of 100 passengers if the group included only 5 silver-haired grandmothers? Formally, what is p x equals 3 using the hypergeometric probability distribution from the formula? X equals 3, A equals 5, N equals 100, the total number of passengers from which those will be drawn for enhanced vetting. N equals 20, the number of passengers that will be selected for enhanced vetting. 5, 3, 95, 17, 120 equals 0. 48. Our conclusion is that the probability of the outcome of 3 of 5 silver-haired grandmothers being randomly selected for additional luggage search is only 0.48. This is only 1/1000th better than drawing 5 cards from a 52-card deck and getting a pair of aces. In short, an unrealistically small probability. A comment here would be that we can with only just under 5% confidence believe that the passengers are selected on a purely random basis. This example demonstrates the ability to answer questions of some interest and policy implication with the use of the tools of probability analysis. Try it for 2. There are a total of 200 balls in a bag. This includes 25 red balls. 40 balls are selected randomly out of the bag. 8 of them are found to be red. Find the relevant probability. A more valuable probability density function with many applications is the binomial distribution. This distribution will compute probabilities for any binomial process. A binomial process, often called a Bernoulli process after the first person to fully develop its properties, is any case where there are only 2 possible outcomes in any one trial, called successes and failures. It gets its name from the binary number system, where all numbers are reduced to either ones or zeros, which is the basis for computer technology and CD music recordings. Binomial formula. nx, letter 1d45d, letter 1d465, letter 1d45e, letter 1d45b minus letter 1d465, where bx is the probability of x successes in n trials when the probability of a success in any one trial is p. And of course q equals 1p and is the probability of a failure in any one trial. We can see now why the combinatorial formula is also called the binomial coefficient, because it reappears here again in the binomial probability function. For the binomial formula to work, the probability of a success in any one trial must be the same from trial to trial, or in other words, the outcomes of each trial must be independent. Flipping a coin is a binomial process because the probability of getting ahead in one flip does not depend upon what has happened in previous flips. At this time, it should be noted that using p for the parameter of the binomial distribution is a violation of the rule that population parameters are designated with Greek letters. In many textbooks, theta pronounced theta is used instead of p, and this is how it should be. Just like a set of data, a probability density function has a mean and a standard deviation that describes the data set. For the binomial distribution, these are given by the formulas. Mu equals np letter 1d70e equals square letter 1d45b letter 1d45d letter 1d45e. Notice that p is the only parameter in these equations. The binomial distribution is thus seen as coming from the one-parameter family of probability distributions. In short, we know all there is to know about the binomial distribution once we know p, the probability of a success in any one trial. In probability theory, under certain circumstances, one probability distribution can be used to approximate another. We say that one is the limiting distribution of the other. If a small number is to be drawn from a large population, even if there is no replacement, we can still use the binomial even thought this is not a binomial process. If there is no replacement, it violates the independence rule of the binomial. Nevertheless, we can use the binomial to approximate a probability that is really a hypergeometric distribution if we are drawing fewer than 10% of the population. En is less than 10% of n in the formula for the hypergeometric function. The rationale for this argument is that when drawing a small percentage of the population, we do not alter the probability of a success from draw to draw in any meaningful way. Imagine drawing from not one deck of 52 cards, but from 6 decks of cards. The probability of, say, drawing an ace does not change the conditional probability of what happens on a second draw in the same way it would if there were only 4 aces rather than the 24 aces now to draw from. This ability to use one probability distribution to estimate others will become very valuable to us later. There are 3 characteristics of a binomial experiment. There are a fixed number of trials. Think of trials as repetitions of an experiment. The letter n denotes the number of trials. The random variable x, number of successes, is discrete. There are only 2 possible outcomes called success and failure for each trial. The letter p denotes the probability of a success on any one trial, and q denotes the probability of a failure on any one trial. P plus q equals 1. The n trials are independent and are repeated using identical conditions. Think of this as drawing with replacement. Because the n trials are independent, the outcome of one trial does not help in predicting the outcome of another trial. Another way of saying this is that for each individual trial, the probability p of a success and probability q of a failure remain the same. For example, randomly guessing at a true-false statistics question has only 2 outcomes. If a success is guessing correctly, then a failure is guessing incorrectly. Suppose Joe always guesses correctly on any statistics true-false question with a probability p equals 0.6, then q equals 0.4. This means that for every true-false statistics question Joe answers, his probability of success p equals 0.6, and his probability of failure q equals 0.4 remain the same. The outcomes of a binomial experiment fit a binomial probability distribution. The random variable x equals the number of successes obtained in the n independent trials. The mean, mu, and variance, sigma 2, for the binomial probability distribution are mu equals np and sigma 2 equals npq. The standard deviation sigma is then sigma equals square root letter 1d45b letter 1d45d letter 1d45e. Any experiment that has characteristics 3 and 4, and where n equals 1 is called a Bernoulli trial, named after Jacob Bernoulli, who, in the late 1600s, studied them extensively. A binomial experiment takes place when the number of successes is counted in one or more Bernoulli trials. Example 4. 3. Suppose you play a game that you can only either win or lose. The probability that you win any game is 55%, and the probability that you lose is 45%. Each game you play is independent. If you play the game 20 times, write the function that describes the probability that you win 15 of the 20 times. Here, if you define x as the number of wins, then x takes on the values 0, 1, 2, 3, 20. The probability of a success is p equals 0.55. The probability of a failure is q equals 0.45. The number of trials is n equals 20. The probability question can be stated mathematically as px equals 15. Letter 1 D443, letter 1 D465 equals 15. Stated more carefully in English would be stated as the probability of exactly 15 wins in 20 trials. Letter 1 D443, letter 1 D465 15 would need again a more careful statement because if we desire letter 1 D443, letter 1 D465 15, we need to calculate all the values of x from p. X equals 0, 1, 2, 14. Similarly, we may wish to know the probability greater than some number, which requires multiple calculations of the values of x. Try it 4. 3. A trainer is teaching a rescued dolphin to catch live fish before returning it to the wild. The probability that the dolphin successfully catches a fish is 35%, and the probability that the dolphin does not successfully perform the trick is 65%. Out of 20 attempts, you want to find the probability that the dolphin succeeds 12 times. Find the px equals 12 using the binomial PDF. Example 4. For problem, a coin has been altered to weight the outcome from 0, 5 to 0, 25 and is flipped 5 times. Each flip is independent. What is the probability of getting more than 3 heads? Let x equals the number of heads in 5 flips of the fair coin. X takes on the values 0, 1, 2, 3, 4, 5. Since the coin is altered to result in p equals 0, 25, q is 0, 75. The number of trials is n equals 5. State the probability question mathematically. Solution px10. First develop fully the probability density function and graph the probability density function. With the fully developed probability density function, we can simply read the solution to the question letter 1 D443, letter 1 D4653 heads. Letter 1 D443, letter 1 D4653 equals letter 1 D443, letter 1 D465 equals 4 plus letter 1 D443, letter 1 D465 equals 5 equals 0. 146 plus 0, 7 equals 0, 153. We have added the two individual probabilities because of the addition rule from probability topics, figure 4. 2 also allows us to see the link between the probability density function and probability and area. We also see in figure 4.2 the skew of the binomial distribution when p is not equal to 0. 5. In figure 4.2, the distribution is skewed right as a result of letter 1 D707 equals letter 1 D45b letter 1 D45d equals 1. 25 because p equals 0. 25. Histogram of probability density function of the given data, figure 4. 2 letter 1 D443, letter 1 D465 equals letter 1 D4650, nx letter 1 D45d letter 1 D465. 1 minus letter 1 D45d letter 1 D45b minus letter 1 D465 equals 5x0. 25 letter 1 D4650, 755 minus letter 1 D4650, etc. Mu equals np equals 1, 25. Try it 4. For a fair six-sided die is rolled 10 times, each roll is independent. You want to find the probability of rolling a 1 more than 3 times. State the probability question mathematically. Example 4.5. Approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. In a statistics class of 50 students, what is the probability that at least 40 will do their homework on time? Students are selected randomly. Problem. This is a binomial problem because there is only a success there are a fixed number of trials and the probability of a success is 0. 70 for each trial, b. If we are interested in the number of students who do their homework on time, then how do we define x? See what values does x take on? D. What is a failure in words? E. If p plus q equals 1, then what is q? F. The words at least translate as what kind of inequality for the probability question p x 40. Solution A. Failure bx equals the number of statistics students who do their homework on time. C. 0, 1, 2, 50. D. Failure is defined as a student who does not complete their homework on time. The probability of a success is p equals 0. 70. The number of trials is n equals 50. Q equals 0. 30. F greater than or equal to the probability question is p x greater or equal to 40. Try it 4. 5. 65% of people pass the state driver's exam on the first try. A group of 50 individuals who have taken the driver's exam is randomly selected. Give 2 reasons why this is a binomial problem. During a certain NBA season, a player for the Los Angeles Clippers had the highest field goal completion rate in the league. This player scored with 61.3% of his shots. Suppose you choose a random sample of 80 shots made by this player during the season. Let x equals the number of shots that scored points. What is the probability distribution for x? Using the formulas, calculate the I-mean and Roman 2 standard deviation of x, find the probability that this player scored with 60 of these shots. Find the probability that this player scored with more than 50 of these shots. There are four main characteristics of a geometric experiment. A trial is repeated until a success occurs. Think of this as one or more Bernoulli trials with all failures except the last one, which is a success. In other words, you keep repeating what you are doing until the first success, then you stop. For example, you throw a dart at a bullseye until you hit the bull's. The first time you hit the bullseye is a success, so you stop throwing the dart. It might take 6 tries until you hit the bull's. You can think of the trials as failure, 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 success, stop. In theory, the number of trials could go on forever. The repeated trials are independent of each other. The probability P of a success and the probability Q of a failure is the same for each trial. P plus Q equals 1 and Q equals 1 minus letter 1 D45D. For example, the probability of rolling a 3 when you throw one fair die is 1/6. This is true no matter how many times you roll the die. Suppose you want to know the probability of getting the first 3 on the 5th roll. On rolls 1 through 4, you do not get a face with a 3. The probability for each of the rolls is Q equals 5/6, the probability of a failure. The probability of getting a first 3 on the 5th roll is 5/6, 5/6, 5/6, 5/6, 1/6 equals 0. 804, the random variable x represents the number of the trial in which the first success occurs. That is, x equals the number of independent trials until the first success. The following are additional attributes of the geometric distribution. The random variable is discrete. The random variable may be defined in two ways depending upon the analyst's interest. In the example above for throwing a die, the question was, what is the probability that the first success will be on the 5th throw? Alternatively, the question could be asked as, what is the probability that it takes 4 failures before a success? We will see that each way of asking the question will alter the form of the geometric probability density function slightly, and will change the mean and standard deviation of the geometric PDF. Implicit in the random variable is that the probability of a success is constant, and therefore so is the probability of a failure. For flipping a coin, this is obvious, but in experiments that require skill, such as hitting a baseball or throwing a dart, one might consider that learning during the experiment would alter the probability of a success. The geometric distribution cannot capture learning, thus the historical probability of success is assumed to be constant. The geometric distribution is memoryless. There are very few probability density functions that are what is known as memoryless, and the geometric distribution is the only one with a discrete random variable that is memoryless. As an example, historically Major League Baseball player Jones has a record of hitting the ball for at least an advance to first base with a probability of 0/20. Jones has not had a hit in his last 10 times at bat. What is the probability that Jones will get a hit in his third time at bat? The answer ignores his 10 previous failures. All events prior to the events in current time are irrelevant and thus are considered memoryless. Formally, letter 1D443, letter 1D465 equals letter 1D45B plus letter 1D458, letter 1D465 greater or equal to letter 1D458 plus 1 equals letter 1D443. Letter 1D465 equals letter 1D45B. Where k equals number of previous failures, Jones's probability of a hit begins anew each time he comes to bat. This feature of the geometric distribution results in a curious result. Drawing parts from a manufacturing process to test for parts that are defective, the geometric distribution begins with a clean slate each time the tests begin with no consideration of previous test results. More on this when we get to the exponential probability density function. Example 4.6, you play a game of chance that you can either win or lose. There are no other possibilities until you lose. Your probability of losing is P equals 0.57. What is the probability that it takes 5 games until you lose? Let x equals the number of games you play until you lose includes the losing game. Then x takes on the values 1, 2, 3, could go on indefinitely. The probability question is P x equals 5, try it 4, 6, you throw darts at a board until you hit the center area. Your probability of hitting the center area is P equals 0.17. You want to find the probability that it takes 8 throws until you hit the center. What values does x take on? Example 4. 7 problem, a safety engineer feels that 35% of all industrial accidents in the plant are caused by failure of employees to follow instructions. They decide to look at the accident reports, selected randomly and replaced in the pile after reading, until they find one that shows an accident caused by failure of employees to follow instructions. On average, how many reports would the safety engineer expect to look at until they find a report showing an accident caused by employee failure to follow instructions? What is the probability that the safety engineer will have to examine at least 3 reports until they find a report showing an accident caused by employee failure to follow instructions? Let X equals the number of accidents the safety engineer must examine until they find a report showing an accident caused by employee failure to follow instructions. X takes on the values 1, 2, 3. The first question asks you to find the expected value or the mean. The second question asks you to find Px greater or equal to 3. At least translates to a greater than or equal to symbol. Solution on average. How many reports would the safety engineer expect to review until they find a report showing an accident caused by something other than failure to follow instructions? This question asks you to find the expected value or the mean. This is the average number of failures from something other than following instructions. The formula for the mean of this geometric distribution is letter 1D707 equals letter 1D438, letter 1D465 equals 1p approximately 2. 8. Note that the mean does not need to be a whole number, although the random variable is discrete, and must be a counting number. What is the probability that the safety engineer will have to examine at least 3 reports until they find a report showing an accident caused by employee failure to follow instructions? This question is answered by first defining the random variable. Let X equals the number of accidents the safety engineer must examine until they find a report showing an accident caused by employee failure to follow instructions. X can take on the values 1, 2, 3, 4, infinity. Unlike the binomial distribution with a fixed number of trials, the geometric distribution may have an infinite number of failed trials before a success occurs. This second question asks you to find letter 1D443, letter 1D465 greater or equal to 3. At least translates to a greater than or equal to symbol. In a binomial distribution, we saw the solution to questions of more than or less than would be to calculate each probability individually and add from 0 to 3. If the probability of interest is greater than or equal to the individual probabilities are added from 0 to 3 and then subtracted from 1. Letter 1D443, letter 1D465 greater or equal to 3 equals 1 minus letter 1D443, letter 1D4653, because we cannot add the full range of the geometric distribution random variable because it goes through infinity, an alternative solution is developed. An alternative geometric distribution pair of formulas provides solutions for questions asking for probabilities more than and less than. If the question is, what is the probability it takes more than n events to get first success? Letter 1D443, letter 1D465, letter 1D45b equals 1 minus letter 1D45d, letter 1D45b. What is the probability it takes less than an event for success? Letter 1D443, letter 1D465, letter 1D45b equals 1 minus letter 1D45d, letter 1D45b. Try it 4. 7. An instructor feels that 15% of students get below a C on their final exam. She decides to look at final exams selected randomly and replaced in the pile after reading, until she finds one that shows a grade below a C. We want to know the probability that the instructor will have to examine at least 10 exams until she finds one with a grade below a C. What is the probability question stated mathematically? Example 4. 8. Suppose that you are looking for a student at your college who lives within 5 miles of you. You know that 55% of the 25,000 students do live within 5 miles of you. You randomly contact students from the college until one says they live within 5 miles of you. What is the probability that you need to contact 4 people? This is a geometric problem because you may have a number of failures before you have the one success you desire. Also, the probability of a success stays approximately the same each time you ask a student if they live within 5 miles of you. There is no definite number of trials, number of times you ask a student. Problem A. Let X equals the number of you must ask. One says yes. B. What values does X take on? C. What are P and Q? D. The probability question is P. Solution A. Let X equals the number of students you must ask until one says yes. B. 1, 2, 3. Total number of students. CP equals 0, 55. Q equals 0, 45. D. P. X equals 4. Try it 4. 8. You need to find a store that carries a special printer ink. You know that of the stores that carry printer ink, 10% of them carry the special ink. You randomly call each store until one has the ink you need. What are P and Q? Notation for the geometric. G equals geometric probability distribution function. Read this as X is a random variable with a geometric distribution. The parameter is P. P equals the probability of a success for each trial. Case I, random variable X is event of first success. In this case we ask, what is the probability that we will have some number X of events of interest to us of failures before a success? The geometric PDF tells us the probability that the first occurrence of success requires X number of failure-independent trials, each with probability 1p. If the probability of success on each trial is p, then the probability that the xdh trial out of x trials is the first success is letter 1 d443, letter 1 d44b equals letter 1 d465 equals 1 minus letter 1 d45d letter 1 d465 minus 1 letter 1 d45d for x equals 1, 2, 3. Like the binomial distribution, the geometric distribution has the parameters of the mean and standard deviation. The expected value of x, the mean for case I, is letter 1d707 equals 1p. This tells us how many failed trials to expect until we get the first success. This count includes in the count of trials the trial that results in success. The above form of the geometric distribution is used for modeling the number of trials until the first success. The number of trials includes the one that is a success. X equals all trials including the one that is a success. This can be seen in the form of the formula. If x equals number of trials including the success, then we must multiply the probability of failure, 1 minus letter 1 d45d, times the number of failures, that is x minus 1. The standard deviation of case I of the geometric distribution is letter 1 d70e equals square 1p minus 1 case II. Random variable x is number of failures before a success by contrast to case I. The following form of the geometric distribution used for modeling number of failures until the first success is letter 1 d443, letter 1 d44b equals letter 1 d465 equals 1 minus letter 1 d45d, letter 1 d465, letter 1 d45d for x equals 0, 1, 2, 3. In this case, the trial that is the success is not counted as a trial in the formula. X equals number of failures. The expected value, the mean of this distribution, is letter 1 d707 equals 1 minus letter 1 d45dp. This tells us how many failures to expect before we have a success. In either case, the sequence of probabilities is a geometric sequence. In case II, the standard deviation parameter is letter 1 d70e equals square 1 minus letter 1 d45dp, bar graph of probability distribution of the given data. Figure 4.3 geometric, p equals 2 common ratio equals r equals 98. The y-axis in figure 4.3 contains the probability of x, and the x-axis is the random number components tested. For example, at x equals 1, the probability it will be found to be defective is 0, 196. With two components tested, the probability the second component is defective is graphed at a probability of 0, 196 at x equals 2 on the x-axis. For the probability that the third component is defective, we find letter 1 d443, letter 1 d44b equals 3 equals 0, 19,208. The first two are the same because of rounding in the computations. Notice in figure 4.3 that the probabilities decline by the same step down with each change in the value of x. This increment is called the common ratio. This exists for the geometric probability distribution uniquely. The common ratio, called r, can be calculated by dividing any value by the previous value, e.g. letter 1 d443, letter 1 d465 equals 5, letter 1 d443, letter 1 d465 equals 4, equals 0, 18,447, 0. 18,823 equals 0. 98 for this set of data, therefore, the common ratio is 0.98. The common ratio then multiplied by any other probability value will provide the next probability value in the sequence. For example, the probability that the sixth component tested is a failure is 0, 18,078. Check this using the formula from case I. Now we have the letter 1 d443, letter 1 d465 equals 6. Knowing this and the common ratio, we can calculate the letter 1 d443, letter 1 d465 equals 7 by simple multiplication. Letter 1 d443, letter 1 d465 equals 7 equals 0. 18,078 times 0.98 equals 0. 17,716, the same value we found earlier by using the geometric probability distribution. This common ratio increment is the same ratio between every number and is called a geometric progression, and thus the name for this probability density function. Once the common ratio is calculated, any letter 1 d443, letter 1 d465 equals letter 1 d465, letter 1 d440 one desires to know can be easily found. The number of components that you would expect to test until you find the first defective component is the mean. Letter 1 d707 equals 50 for this case of defective components. The formula for the mean of the geometric distribution for the random variable, defined as number of failures before first success, is letter 1 d707 equals 1p equals 10. 2 equals 50. See example 4.9 for an example where the geometric random variable is defined as number of trials until first success. The expected value of this formula for the geometric distribution will be different from this version of the distribution. Case II also has a variance but is changed from the case I formula. This formula for the variance is letter 1d443, letter 1d44b equals letter 1d465 equals 1 minus letter 1d45d, letter 1d465 minus 1 letter 1d45d for x equals 1, 2, 3. The formula for the variance is letter 1d70e2 equals 1p minus 1 equals 102, 10. 2. The standard deviation is letter 1d70e equals square 1p minus 1 equals square 10. 2, 10, 2 minus 1 equals 49. 5. This tells us how many failures to expect before we have a success. In either case, the sequence of probabilities is a geometric sequence. Example 4. 9. Assume that the probability of a defective computer component is 0, 2. Components are randomly selected. Find the probability that the first defect is caused by the seventh component tested. How many components do you expect to test until one is found to be defective? Let x equals the number of computer components tested until the first defect is found. X takes on the values 1, 2, 3. Where p equals 0, 2, find px equals 7. Answer px equals 7 equals 10. 027-1 times 0, 2 equals 0, 177. The probability that the seventh component is the first defect is 0. 177. The graph of xg0. 2 is the y-axis contains the probability of x, where x equals the number of computer components tested. Notice that the probabilities decline by a common increment. This increment is the same ratio between each number and is called a geometric progression, and thus the name for this probability density function. See example 4. 10 for an example where the geometric random variable is defined as number of trials until first success. The expected value of this formula for the geometric will be different from this version of the distribution. The formula for the variance is sigma 2, 1p minus 1 equals 102, 10. 2 minus 1 equals 2450. The standard deviation is sigma equals square root 1p minus 1 equals square root 10. 0, 2, 1, 0, 0, 2 minus 1 equals 49. 5. Try it 4. 9. The probability of a defective steel rod is 0. 1. Steel rods are selected at random. Find the probability that the first defect occurs on the ninth steel rod. Use the T83 plus or T84 calculator to find the answer. Example 4. 10 problem. The lifetime risk of developing cancer is about 1 in 67, 15%. Let x equals the number of people you ask before one says they have cancer. The random variable x in this case includes only the number of trials that were failures and does not count the trial that was a success in finding a person who had the disease. The appropriate formula for this random variable is the second one presented above. Then x is a discrete random variable with a geometric distribution. What is the probability that you ask 9 people before one says they have cancer? This is asking what is the probability that you ask 9 people who say no and the 10th person says yes. What is the probability that you must ask 20 people? Find the I-mean and Roman 2 standard deviation of x. Solution letter 1d443, letter 1d465 equals 9 equals 1 minus 0. 0, 15 9 times 0, 15 equals 0. 131 letter 1d443, letter 1d465 equals 20 equals 1 minus 0, times 0, 15 equals 0. 113 mean equals letter 1d707 equals 1 minus letter 1d45d p equals 1 minus 0. 15, 0, 15 equals 65. 67 standard deviation equals letter 1d70 equals square 1 minus letter 1d45d p2 equals square 1 minus 0. 15, 0. 152 equals 66. 16 try it 4. 10 the literacy rate for a nation measures the proportion of people age 15 and over who can read and write. The literacy rate for women in the United Colonies of Independence is 12%. Let x equals the number of women you ask until one says that she is literate. What is the probability distribution of x? What is the probability that you ask 5 women before one says she is literate? What is the probability that you must ask 10 women? Example 4. 11 a baseball player has a batting average of 0, 320. This is the general probability that he gets a hit each time he is at bat. Problem: what is the probability that he gets his first hit in the third trip to bat? Solution: p x equals 3 equals 10. 32 3-1 times 32 equals 0 1480. In this case, the sequence is failure, failure, success. Problem: how many trips to bat do you expect the hitter to need before getting a hit? Solution: letter 1d707 equals 1p equals 10. 320 equals 3. 125 approximately 3. This is simply the expected value of successes and therefore the mean of the distribution. Try it 4. 11. A runner has a probability of 0.426 to come in first in a race. What is the probability that they will come in first in the fourth race? How many races do you expect the runner to need before they come in first? Example 412 problem. There is an 80% chance that a Dalmatian dog has 13 black spots. You go to a dog show and count the spots on Dalmatians. What is the probability that you will review the spots on 3 dogs before you find one that has 13 black spots? Solution P x equals 3 equals 1083 times 080 equals 064. Try at 412. There is a 75% chance that a parrot is green. You go to a pet shop and observe the parrots. What is the probability that you will observe 4 parrots before you find one that is a green parrot? Another useful probability distribution is the Poisson distribution, or waiting time distribution. This distribution is used to determine how many checkout clerks are needed to keep the waiting time in line to specified levels, how many telephone lines are needed to keep the system from overloading, and many other practical applications. A modification of the Poisson, the Pascal, invented nearly 2 centuries ago, is used today by telecommunications companies worldwide for load factors, satellite hookup levels, and internet capacity problems. The distribution gets its name from Simeon Poisson, who presented it in 1837, as an extension of the binomial distribution, which we will see can be estimated with the Poisson. There are 2 main characteristics of a Poisson experiment. The Poisson probability distribution gives the probability of a number of events occurring in a fixed interval of time or space if these events happen with a known average rate. The events are independently of the time since the last event. For example, a book editor might be interested in the number of words spelled incorrectly in a particular book. It might be that, on the average, there are 5 words spelled incorrectly in 100 pages. The interval is the 100 pages, and it is assumed that there is no relationship between when misspellings occur. The random variable x equals the number of occurrences in the interval of interest. Example 413. Problem. A bank expects to receive 6 bad checks per day on average. What is the probability of the bank getting fewer than 5 bad checks on any given day? Of interest is the number of checks the bank receives in one day, so the time interval of interest is 1 day. Let x equals the number of bad checks the bank receives in one day. If the bank expects to receive 6 bad checks per day, then the average is 6 checks per day. Write a mathematical statement for the probability question. Solution Px5. Try at 413. An electronics store expects to have 10 returns per day on average. The manager wants to know the probability of the store getting fewer than 8 returns on any given day. State the probability question mathematically. Example 414. You notice that a news reporter says on average 2 times per broadcast. What is the probability that the news reporter says more than 2 times per broadcast? This is a Poisson problem because you are interested in knowing the number of times the news reporter says during a broadcast. Problem. A. What is the interval of interest? Solution. A1 broadcast measured in minutes. Problem. B. What is the average number of times the news reporter says during one broadcast? Solution. B2. Problem. C. Let x equals what values does x take on? Solution. Let x equals the number of times the news reporter says during one broadcast. X equals 0, 1, 2, 3. Problem. D. The probability question is P. Solution. DPX2. Try it 414. An emergency room at a particular hospital gets an average of 5 patients per hour. A doctor wants to know the probability that the ER gets more than 5 patients per hour. Give the reason why this would be a Poisson distribution. Notation for the Poisson: P equals Poisson probability distribution function. X p mu. Read this as x is a random variable with a Poisson distribution. The parameter is mu or lambda. Mu or lambda equals the mean for the interval of our interest. The mean is the number of occurrences that occur on average during the interval period. The formula for computing probabilities that are from a Poisson process is letter 1 d443 letter 1 d465 equals letter 1 d707 letter 1 d465 letter 1 d452 minus letter 1 d707. X, where px is the probability of x successes, mu is the expected number of successes based upon historical data, e is the natural logarithm approximately equal to 2. 718 and x is the number of successes per unit, usually per unit of time. Remember your algebra class, letter 1 d465 minus letter 1 d45b equals 1. Letter 1 d465 letter 1 d45b. The Poisson distribution has both a mean micro, the average number of occurrences per unit of time, and also a standard deviation, letter 1 d70 equals square letter 1 d707. In order to use the Poisson distribution, certain assumptions must hold. These are, the probability of a success mu is unchanged within the interval, there cannot be simultaneous successes within the interval, and finally that the probability of a success among intervals is independent, the same assumption of the binomial distribution. In a way, the Poisson distribution can be thought of as a clever way to convert a continuous random variable, usually time, into a discrete random variable by breaking up time into discrete independent intervals. This way of thinking about the Poisson helps us understand why it can be used to estimate the probability for the discrete random variable from the binomial distribution. The Poisson is asking for the probability of a number of successes during a period of time, while the binomial is asking for the probability of a certain number of successes for a given number of trials. Example 4. 15. Lee receives about 6 telephone calls between 8 a.m. and 10 a.m. What is the probability that Lee receives more than one call in the next 15 minutes? Let x equals the number of calls Lee receives in 15 minutes. The interval of interest is 15 minutes or 1 hour. X equals 0, 1, 2, 3. If Lee receives on the average 6 telephone calls in 2 hours, and there are 8 15-minute intervals in 2 hours, then Lee receives 6 equals 0, 75 calls in 15 minutes on average. So mu equals 0, 75 for this problem. Find px1. The Poisson distribution is discrete and thus one includes all whole numbers through infinity. The solution is to subtract the probability less than 1, thus 1 minus letter 1d443. Letter 1d465 equals 0, plus letter 1d443, letter 1d465 equals 1. Letter 1d443, letter 1d465 equals letter 1d707, letter 1d465, letter 1d452, minus letter 1d707. Letter 1d443, letter 1d4651 equals 1 minus letter 1d443, letter 1d465 less or equal to 1. Equals 1 minus letter 1d443, letter 1d465 equals 0 plus letter 1d443, letter 1d465 equals 1. Equals 1 minus 0, 750 letter 1d452 minus 0, 75. 0 plus 0, 751 letter 1d452 minus 0, 75. 1 equals 1 minus 1, 0, 4724. 1 plus 0, 75, 0, 4724. 1 equals 1 minus 0, 4724 plus 0, 3543 equals 0. 1733. Histogram of probability distribution of the given data, figure 4.4. The y-axis in figure 4.4 contains the probability of x, where x equals the number of calls in 15 minutes. Try at 4.15. A customer service center receives about 10 emails every half hour. What is the probability that the customer service center receives more than 4 emails in the next 6 minutes? Example 4. 16. According to Baden, an email management company, an email user gets, on average, 147 emails per day. Let x equals the number of emails an email user receives per day. The discrete random variable x takes on the values x equals 0, 1, 2. The random variable x has a Poisson distribution, xp147. The mean is 147 emails. Problem. What is the probability that an email user receives exactly 160 emails per day? What is the probability that an email user receives at most 160 emails per day? What is the standard deviation? Try at 4.16. According to a recent poll by the Pew Internet Project, people between the ages of 14 and 17 send an average of 187 text messages each day. Let x equals the number of texts that a girl aged 14 to 17 sends per day. The discrete random variable x takes on the values x equals 0, 1, 2. The random variable x has a Poisson distribution. X tilde p 187. The mean is 187 text messages. What is the probability that a person sends exactly 175 texts per day? What is the probability that a person sends at most 150 texts per day? What is the standard deviation? Example 4.17. Text message users receive or send an average of 41. 5 text messages per day. Problem. How many text messages does a text message user receive or send per hour? What is the probability that a text message user receives or sends 2 messages per hour? What is the probability that a text message user receives or sends more than 2 messages per hour? Try at 4.17. Atlanta's Hartsfield-Jackson International Airport is the busiest airport in the world. On average, there are 2,700 arrivals and departures each day. How many airplanes arrive and depart the airport per hour? What is the probability that there are exactly 100 arrivals and departures in 1 hour? What is the probability that there are at most 100 arrivals and departures in 1 hour? Example 4.18. Problem. On a specific day in May starting at 4. 30 p.m., the probability of low seismic activity for the next 48 hours in Alaska was reported as about 1–2%. Use this information for the next 200 days to find the probability that there will be low seismic activity in 10 of the next 200 days. Use both the binomial and Poisson distributions to calculate the probabilities. Are they close? Solution. Let x equals the number of days with low seismic activity, using the binomial distribution. Letter 1D443, letter 1D465 equals 10 equals 210 times 10,210 times 9,898,190 equals 0, 39. Using the Poisson distribution, calculate mu equals NP equals 200, 0. 102 approximately 2, 4. Letter 1D443, letter 1D465 equals 10 equals. Letter 1D707, letter 1D465, letter 1D452. Legs equal 20410, letter 1D452 minus 2, 4. 10 equals 0, 45. We expect the approximation to be good because n is large greater than 20, and p is small less than 0. 5. The results are close, both probabilities reported are almost 0, try at 4:18. On a specific day in May starting at 4:30 p.m., the probability of moderate seismic activity for the next 48 hours in the Kuril Islands off the coast of Japan was reported at about 1.43%. Use this information for the next 100 days to find the probability that there will be low seismic activity in 5 of the next 100 days. Use both the binomial and Poisson distributions to calculate the probabilities. Are they close? Example 419. The Poisson distribution is often referred to as a waiting time distribution. In a sense, this is tied to the link between the discrete distribution measuring the number of occurrences and the treatment of the continuous random variable time. The Poisson takes the continuous random variable time and breaks it into a discrete random variable by measuring the discrete number of occurrences. In example 4:16, we were measuring the number of messages sent, an occurrence, a discrete random variable per day, a continuous random variable. The Poisson distribution can be used for many other applications. Any continuous random variable that can be broken into discrete measures can use the Poisson distribution to calculate probabilities of the number of a given discrete value of x, the number of occurrences in which we have an interest. We are interested in the number of potholes in a highway to evaluate the quality of the paving job. In this case, the pothole is the occurrence and can be counted per square miles of highway. Mile is a continuous random variable, and potholes is the discrete random variable. We may want to know the probability that a particular paving technique results in more than 20 potholes in 10 miles of paving. If that is the case, we may discard that paving technique. Alternatively, our chocolate cookies claim that each cookie has more than 5 chocolate pieces in each cookie. Sampling the cookie dough, we can calculate the probability that the resulting cookies will meet the claim of 5 chocolate pieces per cookie. Perhaps the production of glass for automobile windshields suffers from a flaw known as the dot. In the production process, air infrequently becomes lodged in the hot glass and upon cooling leaves a dot that distracts the driver. This would also be a case where use of the Poisson probability distribution would be the appropriate tool. To calculate the probability that the results have fewer than 3 dots, the number acceptable to the manufacturing process, the Poisson distribution would be useful. By way of warning, the Poisson is a discrete random variable. We are counting occurrences. It occurred or it did not during the time, the miles of road, or the batch of cookie dough. In this sense, the Poisson is like the binomial in that the occurrence is binary, happened or did not. Because of this link to the binomial, we can use the Poisson to estimate a binomial distribution, and this is discussed below. Try at 419. In a small city, a survey 500 vehicles reveals that there is a 2% chance of an accident occurring in a week. Calculate the probability that at most 2 accidents occur in any given week, estimating the binomial distribution with the Poisson distribution. We found before that the binomial distribution provided an approximation for the hypergeometric distribution. Now we find that the Poisson distribution can provide an approximation for the binomial. We say that the binomial distribution approaches the Poisson. The binomial distribution approaches the Poisson distribution is as n gets larger and p is small such that np becomes a constant value. There are several rules of thumb for when one can say they will use a Poisson to estimate a binomial. One suggests that np, the mean of the binomial, should be less than 25. Another author suggests that it should be less than 7. And another, noting that the mean and variance of the Poisson are both the same, suggests that np and npq, the mean and variance of the binomial, should be greater than 5. There is no one broadly accepted rule of thumb for when one can use the Poisson to estimate the binomial. As we move through these probability distributions, we are getting to more sophisticated distributions that, in a sense, contain the less sophisticated distributions within them. This proposition has been proven by mathematicians. This gets us to the highest level of sophistication in the next probability distribution, which can be used as an approximation to all of those that we have discussed so far. This is the normal distribution, example 420. A survey of 500 seniors in the Price Business School yields the following information. 75% go straight to work after graduation. 15% go on to work on their MBA, 9% stay to get a minor in another program, 1% go on to get a master's in finance. Problem. What is the probability that more than 2 seniors go to graduate school for their master's in finance? Solution. This is clearly a binomial probability distribution problem. The choices are binary when we define the results as graduate school in finance versus all other options. The random variable is discrete and the events are, we could assume, independent. Solving as a binomial problem, we have binomial solution. Letter 1D45B, letter 1D45D equals 500 0. 0, 1 equals 5 equals micro. Letter 1D4430 0 equals 500 0, 500 minus 0, 0, 0, 10, 1 minus 0. 0, 1, 500 minus 0 equals 0, 657. Letter 1D443 1 equals 500 1, 500 minus 1, 0, 0, 11, 1 minus 0. 0, 1, 500 minus 1 equals 0, 3318. Letter 1D443 2 equals 502, 500 minus 2, 0, 0, 12, 1 minus 0. 0, 1, 500 minus 2 equals 0, 8363. Adding all three together equals 0, 12,330. 1 minus 0, 12,339 equals 0, 87,661. Poisson approximation. Letter 1D45B, letter 1D45D equals 500 0. 0, 1 equals 5 equals letter 1D707. Letter 1D45B, letter 1D45D, 1 minus letter 1D45D equals 500 0, 0, 1, 0. 99 approximately 5 equals letter 1D70, 2 equals letter 1D707. Letter 1D443, letter 1D44B equals letter 1D452 minus letter 1D45B, letter 1D45D, letter 1D45B, letter 1D45D, letter 1D465. Legs equals letter 1D443, 0 equals letter 1D452 minus 550. 0 plus letter 1D443 1 equals letter 1D452 minus 551. 1 plus letter 1D443 2 equals letter 1D452 minus 552. 2 0 67 plus 0 337 plus 0 1247. 1 minus 0 1247 equals 0 8753. An approximation that is off by 1/1000th is certainly an acceptable approximation. Try it 420. In example 420, what is the probability that less than 4 seniors will go to graduate school for their master's in finance?